consider two masses coupled to each other with via springs. Via a spring. Say. So this is the picture. You have one spring, a spring constant little k. There's a mass m, and there is a coupling spring of spring constant kappa, and there is a mass m over here, and there's a spring of spring constant k. And we are considering two identical masses. Now the force on the first mass for the, where the displacement x1 corresponds to the displacement of the first mass. So this is the notation I'm using for that. And that is clearly, what is it going to be? Minus kx1. And in addition, there is a minus kappa x1, right? Now, the force on the first mass, when there is a displacement x2 of the second mass, is F1 is what? Kappa is the spring constant of the spring that is coupling these two oscillators. So here, what should I? Okay. No, for the moment it's x1. It's the due to the displacement x1. What is the force on what? I'll stick to kappa because I've done the rest of the algebra. Okay. So so what should I write here? This is force on the first mass when there is a displacement x2 of the second mass. X2 is correct, but kappa, because that's the coupling. So the first mass will be affected by the displacement of the second mass only via the coupling. So therefore, what will come here is kappa. Okay, so given this, what are the equations of motion? Newton's second law. Are, so if I write, I'll just writing the left-hand side. How shall I write what is the right-hand side based on these two? Exactly, yeah. Correct, yeah. So minus kx1 minus kappa x1 plus kappa x2, right? And can you guess what would be the equation of motion for pertaining to x2 now? So is there a simple way to see what will happen to this equation? Suppose you take the first equation. Correct. So 1 and 2 get swapped. So you'll basically get that, right? In other words, and I'll write it more concisely. If I collect everything, I'll just get Okay, so now what is the first feature that you observe about these equations that makes it look somewhat complicated? Sorry? Yeah, linear, all those things are there. But what is the feature that appears to make it somewhat complicated? Yeah, they're coupled. The equations are coupled. So the x1 equation involves both x1 and x2. Likewise, x2 equation involves both x1 and x2. So can you suggest a method by which I can simplify this problem? Exactly. Okay, yeah, sorry. Yeah, very good. Correct, yeah. Yeah. So the one easy way to see how you can simplify the equations is what she was suggesting is you go to what I call this addition and subtraction is a center of mass variable, which you are familiar with, the notion of center of mass. So this is basically x1 plus x2 by 2 and a relative coordinate, which is x1 minus x2. If you do this, you'll see that you end up with equations of this form. You see cancellations happening, which I leave you to check. So if you think in terms of the variable, this center of mass variable is basically right. So it looks like an independent oscillator. It's very simple to solve. And so likewise, you can show that if you write in terms of the, so likewise you can also get an equation for the relative coordinate. And what I leave it to you to fill it up. But what I want to say is that if you take this, can you suggest a solution for this one? The first one? Cosine, or, yeah. So I'll just write it in terms of a cosine. So I'll say that I'll just write it like this. And likewise, for the relative coordinate, you find okay. So yeah, sorry, yeah. What happened? What are the? What is the meaning of the notation? Yeah, this is the force on the first mass, yeah, due to the displacement x1. And I've just broken it up. You could have written the whole thing in one shot, but it just offers more clarity if we just divide it. Sorry? Yeah, it's basically if you are displacing it like this, it will tend to come back. Yeah, yeah. Right. Yeah, I think x1 will be like this. Imagine doing like this, and this one is like this. Like that. Okay, so one thing you notice when I write this thing, oh, sorry. Oh, yeah. Yeah, the sign error. Yeah, it should be like this, I think. Let's see if it makes sense. If you pull it like this, then minus kx1. Yeah, x2 is like this. So, yeah. Oh, I see, I see. Okay. Oh, yeah, it's very far from that there. Can you, yeah, maybe you don't have to sit all in one, on the same line for just for this lecture. Mm-hmm. No, it's, if you pull it like this, it will tend. Yeah. Sorry, where is it?
No.
It's clear, okay. Okay, so here, I've written this, and where omega s is square root of k over m, and omega sub f equals square root of k plus 2 kappa over m. So I've used two subscripts, s and f. Why have I used them? Slow and fast. Yeah, slow and fast, because this frequency, omega s, is clearly less than omega f, right? So what happened is that by doing this, going into a situation where we express the system in terms of sums and differences, we find the two decoupled equations, and these are what are called the normal modes of the system. And these are the normal frequencies, the eigenfrequencies pertaining to that. So a normal mode analysis enables you to look at the system from the point of view of two independent oscillators, even if you start with a system which is coupled. So that's the advantage of a normal mode analysis. This one? Okay, this one, I've just taken those two equations, take the left-hand side, add it. That's all I have done. I'll take the right-hand side, add. That's all. This one, I leave it to you to fill in. Yeah. Yeah. Correct. Exactly. That's correct. Yeah, yeah. In fact, the normal mode, because of the dividing it up into the normal modes, we can go back to finding what the individual x1 and x2 are, precisely because of that. Okay? So at this point, I want to say that what we have achieved here is essentially a diagonalization of a 2 by 2 matrix. So even though I haven't introduced matrices, this is effectively what we have achieved. Starting from a matrix which has all non-zero elements, we have ended up with a matrix which has only diagonal elements. How many of you are exposed to matrices? Yeah, quite a large number. Yeah, I think perhaps also because some of you have also encountered quantum mechanics, right? Apart from, so that's actually matrix mechanics. Okay. So anyway, it doesn't hurt to go over this stuff. Okay. So yeah. So as you pointed out, that can we find out what x1 and x2 are doing individually. So indeed, you can do that by taking some linear combinations of the center of mass and the relative coordinates, right? So if I write it, you can check for yourself by doing that algebra. Yeah, I leave it to you. Homework exercise is cos omega st plus phi s plus af cos omega ft plus phi f, right? So you have got x1, and likewise you can also get x2. Okay? So that answers your question. Okay, so now let us recast the same problem in matrix form. So now let us consider two distinct masses, M1 and M2. In fact, you can extend it to any number of masses, say n masses and n springs, and generalize the idea. That's the power of going to a matrix representation, right? But here, for the sake of concreteness and illustration and simplicity, we'll restrict ourselves to only two masses coupled by a spring. Yeah. So we consider again a two-mass system. The only difference is, let's consider M1 and M2 to be different. M1 and M2 instead of M1 equal to M2 equals M. Okay? And there we tried out a cosine solution, and you can check that it works. It's actually more convenient to introduce exponential notations. So for instance, consider solutions of the form x1 equals c1 e to the power I omega t, and x2 c2 e to the I omega t. These exponentially oscillating functions, right? So these have connections to Fourier transforms, and I won't talk about it because Rajaram is going to cover Fourier transforms. So this has close connections to Fourier transforms. So plugging these solutions into our earlier equations, these Newton's equations, second law, we get and I should put M1. I'm distinguishing the two masses. Right? And this can be cast in a matrix form, which I'll write here. Okay. So the matrix under consideration, the 2 by 2 matrix, is of this form. You can convince yourself about this looking at the equation. A plus kappa over M1, kappa over M1, kappa over M2, and K plus over M2. Right? This is a 2 by 2 matrix, and we can write it in a succinct manner by using matrix notations, actually notations borrowed from quantum mechanics, which was introduced by Dirac. That makes things very simple and elegant. So we can write that same system in this form. M C equals minus omega square C. Does this make sense? Okay, I should write what C is. C is a C ket, is a ket vector, is of the form C1, C2. It's a column vector with 2 entries, right? So does this remind you of something that you have learned, this thing? Harmonic oscillator, all right, but more generally, if you have a structure, eigenvalue equation. So you have encountered them in quantum mechanics. And quantum mechanics has a linear Hilbert space structure, a linear vector space structure. So everything is linear, and the reason why there is a similarity between this system and quantum mechanics is because this is a linear classical system, right? So that's what this is, eigenvalue equation. And so in general, if we have an n by n system, we can write, suppose the n by n matrix looks like this, A, and the vector V equals lambda V. This is the eigenvalue equation pertaining to that. And then we can rearrange and write it as A minus lambda 1 V equals 0, right? So if I want to solve this system, one of the solutions is a trivial solution. So what is the trivial solution? Yeah, and that comes from taking an inverse of this and multiplying with it. So V equal to 0 is the trivial one. We are not interested in that. And if we want to get non-trivial solutions, what do we do? Yeah, you take you demand that the determinant in this particular case, now let's leave this aside, although I was generalizing. Let's go back to our problem. So then in our problem, the corresponding thing is M C equals minus omega square C. Then the non-trivial solution corresponds to this, what they call secular determinant, 0. And if you plug those things in, that matrix I've already written over there, right? So what would this give rise to? If I do this, if I take the determinant, So it's the determinant of this. Oh, so the determinant of this thing is equal to 0. And I suppose many of you know how to compute the determinant. So what would be the determinant of this equation, of this matrix? If you take a matrix A, B, C, D, then that's right. So if you do that and then set it equal to 0, right? What you'll end up with, I think I'll write it there. Maybe I can write it here itself. What do you expect to get? I mean, the structurally? What kind of equation do you expect to get? A quadratic equation, right? So you end up with right? And you can check for yourself. For us, one interesting case is M1 equal to M2 equal to M, right? Because this is a case that we have already done. So let's check if that is borne out. So in fact, this is what you would get in that situation. And you can check for yourself that you recover those slow and fast frequencies. These are the two solutions, omega 1 and first and second solutions. Right? So this is an explicit way of checking that this works out. Now, the other issue of diagonalization of the matrix. So we have got the eigenvalue equation, and we have got those normal modes. So I'll just summarize what one does for diagonalization, which I think many of you perhaps already know. So given M, find out the eigenvalues the way we did already. Lambda I equals 1 and 2 possibilities. Then given lambda I, find out eigenvectors. That you do via the eigenvalue equation. Right? Then you construct a matrix with the eigenvectors like this. So here there are two eigenvectors, V1, because V1 1 and V1 2, right? And or I can use this. You can either use it like this or this way. It's fine. Then So you place the eigenvectors in this manner. So you just write so you have a matrix that you have constructed, and then you find out the inverse of the matrix that you know how to do, right? And then construct the diagonal matrix in this manner. So that's the diagonalization procedure. So do you know how, does everybody know how to compute the inverse? Just one illustration I'm giving you. So if you have A equals ABCD, then A inverse will be this. Sorry, yeah. So, okay. So, one thing I wanted to say now is something that we have been harping on from the beginning of this summer school, that this is a relatively lowbrow textbook problem, and it's interesting because you are doing coupled oscillator experiments, so you see connections between theory and experiment. That in itself is very rewarding. But physics, the beauty of physics is that the power of connectivity, the power to connect and go much beyond the small problem, the relatively mundane problem that you're looking at. So as it turns out that this coupled oscillation, problem of coupled oscillations has a very interesting fundamental application. And that has to do with neutrino oscillations. Have you heard of neutrino oscillations? Yeah. Has anybody heard of neutrino oscillations? I think you have. I had met you at Copy with Curiosity and we've discussed. Okay. So neutrino oscillations is a very interesting phenomenon. So what happened is that it stemmed from the fact that there was an interesting mystery that needed to be solved. So as it turns out that neutrinos are fundamental particles, and these are emitted by the sun. So what was observed is that theoretically there was a certain expectation of the number of neutrinos that would be detected on the Earth coming from the sun. But when they actually detected, they found about 1/3 of the number. So how to make sense of that? So they had to go beyond this standard understanding, and then they realized that neutrinos are characterized by a quantum number called flavor, and there are flavor oscillations happening, because of which that accounts for the fact that the number that you're getting is lower. So suppose you have, there are 3 flavors of neutrinos. Electron, muon, and tau neutrinos. So if you have a detector which is sensitive to electron neutrinos, and you find that you have a certain estimate and you find something much less than that. So what is happening actually is that in the process of propagating from the sun to the Earth, there are oscillations happening where the neutrino goes from one flavor state to another. And hence, what you get is, in terms of the electron neutrino count, is much smaller. So, sorry? Mm-hmm. Yeah, there are masses, that's the thing. In the standard model, the neutrinos, you assume that neutrinos don't have masses. So this forces you to realize that neutrinos have masses. Yeah. Yeah, so we'll discuss that, okay? So we won't go very deep into neutrino physics, but we'll discuss something related to mass eigenstates. So the thing is that when you have a complicated structure, in theoretical physics, it's often helpful to go to a simpler structure, and if you can understand it there, that's good enough. I mean, if something captures the essence of it, that's good enough. So you don't really need to deal with all three flavors. Suppose we restrict to only 2 neutrino flavors, right? So let's consider the 2-flavor neutrino model. So if we restrict to that, so now I think you're already probably realizing the connection with the problem that I had discussed earlier. So you are actually dealing with a 2-state system. So a flavor state, a typical, you can schematically write a flavor state. Now this is where the mass eigenstates would come up. You can write a flavor state as a linear combination of 2 mass eigenstates. This is just a schematic, just to give an understanding of this thing. So in the mass eigenbasis, you can expand the flavor state in this manner. This is actually completely analogous to something that happens in polarization optics. So this is another point that we keep mentioning, that different parts of physics get very easily connected. You don't have to work that hard. So this is what happens is that polarization, what is polarization? Let's go over that first. It connects to polarized light. In the context of polarized light, there is some phenomenon that happens that it can. So what is polarization? Yeah. Does anyone want to answer? What is it? Yeah. What is it associated with? Yeah. That's what is polarizing something, yeah. So what happens is that the electromagnetic wave is a transverse wave. So there's a propagation direction, and perpendicular to the propagation direction, there are the 2 directions. There are electric and magnetic fields which oscillate. Now, if you keep track of the oscillations of the electric field, you're keeping track of the polarization. That's what it is. So as it turns out that in the context of polarized light, there are various kinds of polarized light you may have heard of. Circularly polarized light or linearly polarized light and so on. So there is a very neat thing. I'll just 1 second. I want to show this. This is nothing special, but I'll show it nevertheless. So this is a sphere, right? So as it turns out that you can represent all polarization states on a sphere, and that is called the Poincare sphere. And Poincare sphere, I'll go over it a little bit more in detail, but it's nice to see it and just remember certain things about it. The north and the south poles represent circularly polarized lights. So the north pole is right circularly polarized light, south pole is left circularly polarized light, and you can see a rim of this ball, right? So this is the equator. On the equator, all the linearly polarized states live on the equator. So, and in general, if you take an arbitrary point, those are elliptically polarized light representation. So, there is a connection between this and that. In particular, just to make it look similar, I'll just say that if you take a linearly polarized state, you can write it as a linear combination of circularly polarized states. So right circularly polarized light and left circularly polarized light, and if you take the linear combination of that, you get a linearly polarized light. So you can right away see that a flavor state has correspondence with a linearly polarized state, and the mass eigenstates, mass basis states that we had expanded the flavor state in terms of, correspond to the circularly polarized states, right? So on the Poincare sphere, what it means is that given a state on the equator, you can write it as a linear combination of these two states. So all points of the equator, sorry? These are only restricted to linear states. I have here only, this is a linearly polarized light state, and I'm expanding it as a linear combination of two circularly polarized lights. Okay. So states on the equator of the Poincare sphere. So you can see, or right away, I think you can start to guess that there may be some connection between flavor oscillations and oscillations, rotation of linearly polarized light on the Poincare sphere. So I'll just go a little bit more into detail of the Poincare sphere representation so that the two-state system structure comes out better. So you were asking what about an arbitrary state, right? So an arbitrary, it turns out it's convenient to write an arbitrary state, polarization state, in this form. Okay? So this is a phase factor, and this is the polar angle, and this is the azimuthal angle. And it's interesting, the half angles come into play. Okay, so then what you do is that let's make it a bit simple. Let's not keep too many extra stuff. And say that we'll get rid of the overall phase and have this cosine theta by 2 e to the power minus I phi by 2 and sine theta by 2 e to the I phi by 2, right? Which can be further simplified to make it look like 1 tan theta by 2. I've taken out overall stuff here, e to the I phi, right? So this actually brings us to a very interesting point. This particular representation is basically what we can write as 1z, where z is a number in the complex plane. So z equals r e to the I phi with r, where r equals tan theta by 2. And this is actually what is telling us is a representation of the sphere on the complex plane. So this is called stereographic projection. So it's also sort of connected to the talk that I had given yesterday on math and art, projective geometry. So if now, sorry, yeah, something, yeah. Mm-hmm. Yeah. Yeah, and also it's going to be it's being transmitted. People will know what is happening.
Hello.
Yeah.
What is that n and eta in size equation?
Yeah, you can just actually forget about this. This is like a normalization factor, and this is an overall phase. This is a phase no different from these things, but here there's a meaning to it. This is a polar angle and there is a azimuthal angle. This is an overall phase, which I am ignoring because I just want to focus. This is basically on the sphere. When you look at the Poincare sphere or the block sphere, you are actually representing psi back to back. So the phases get to be irrelevant. It's a space of density matrices. So the pure states are on the, because you, sorry? No, it's not negligible. Let it be there. But finally, what we will be concerned with is an object of this kind, where it will cancel out. Because this one and its complex conjugate. Yeah. Yeah.
This is a vector space, and if she's interested in the direction, she can prove an overall factor from that vector. So some multiple of this vector. And this vector happens to be a unit vector, which is on the surface of the point. But there she chooses to choose a non-unit vector. The second one here is a non-unit vector.
Yeah. So the thing is that actually this particular thing, I'm just going a little bit beyond the thing, that you take that sphere that I had shown, or the sphere that I had shown in yesterday's talk, the block sphere. That is the representation is of this object, psi back to back. It's called a density matrix. So when you take this and its complex conjugate back to back, this factor would go away. That's part of the reason. That's the reason why we are not looking at it. Yeah. Yeah. So you can make identifications, right? I've taken out this cosine theta by 2 and e to the minus the whole thing out, and I get this thing. Now it's convenient to think of it as basically we know in this Argand, I think they call it Argand's diagram or something like that, right, in electrical engineering, is e to the I phi. This is a representation in the complex plane. So this tan theta by 2 plays the role of R. That's what happens. And you will find that in this kind of representation, the north pole, what I showed with that smiley ball, the Poincare sphere, north pole goes to 0, and the south pole goes to infinity. These are all things I'm leaving you to check. But I wanted to show something. Yeah. Okay. So this is something that was 3D printed by Disha. No, Disha had done it for us, made this sphere with a thing taken out. And now I'm doing something. Yeah. What do you see? It's like a coordinate chart on the two-dimensional plane, right? So this is basically what we were talking about. It's a representation of the sphere on the plane. And what has been done, you actually have taken out one pole. Here it's the south pole, and you have placed the light source there, and you're getting a projection on the plane. So this demo is an experiment version of this mathematical fact that we are mapping the sphere minus a point to onto the complex plane. So maybe we can go further. Yeah. So now we discuss, now it's very clear that there is a connection between neutrino oscillations and Poincare sphere because of all these connections which we have made. Now let's see what further we can say. This is the projective stereographic projection part of it. Now, as many of you will be familiar with polarization optics. So suppose I take a plane polarized light and pass it through a sugar solution. What happens? It rotates, exactly. So now if it goes from one linear state to another and it keeps rotating like that, that is equivalent to saying the linear states are oscillating. That is completely analogous to the statement that the flavor states undergo oscillations. So we'll see a demo now. I will try to do this first, then this one, the light is the light from backlight. This is on on. Okay. Lamp is on. I think looks like something's coming. Yeah. Some? Yeah, from bottom. Okay. It was there. Here, it's there. Yeah. That's there. Okay. And we have to project it here. And this is it's focused. Yeah. So we have a polarizer there at the bottom, and this sugar solution, and I've put one Polaroid, and now I'm turning it. What do you see? Change in color. Yeah, so this is basically an analog neutrino oscillation experiment. Polarization optics analog of neutrino oscillations. Maybe we can also play the video. So this.
Ma'am,
Yeah.
what was that thing above that which you were rotating?
Oh, this is a Polaroid. It's like it's exactly the experiment that somebody was mentioning about sugar solution. So you have light incident on a polarizer. That's what is there at the bottom. Then there is this sugar solution, and this is the second polarizer. So this is like I think they call it analyzer, right? One is a polarizer, then an analyzer. So as you're turning the analyzer, you're going from one linearly polarized state to another, and you see these colors coming out. So, and this is an exact analog of neutrino oscillations, because both are two-state systems, and there's an exact mapping between these. In fact, if you want to understand it in more detail, I urge you to look at Poonam Mehta's paper. It's called Topological Phases, I think, in neutrino oscillations. You can just type these keywords in and you'll find it. So they're the, what is it? Yeah, this is basically because it's, first of all, if you have two, suppose I have two Polaroids, right? And if I keep rotating them, at some point I'll see that there is a complete cancellation, right? If they are cross-polarized. On the other hand, if you put the sugar solution in the middle, you find that light passes through. And that is because the sugar solution rotates the polarization state, right? So something that was not passing through, some part of it will pass through. And then as you are rotating the second polarizer, you are basically letting out different polarization states. You're going from one polarization state to another polarization state, and that is effectively equivalent to neutrino oscillations. This is if you look at that sphere. Sorry. So, shall I repeat it? Yeah. So basically, as you are rotating the Polaroid, you're letting in. If you have a complete cancellations, first of all, if you take two cross Polaroids, you can come to a point where there's complete cancellation, and then you put the sugar solution, and you find that it lets out light, because these if you can think of the linear polarization as being made up of a superposition of circular polarization states, and the two circular polarization states acquire a relative phase, leading to a rotation of the linear polarization. That's what you know. And now if I keep turning this analyzer, I am basically effectively what you're seeing is going from one linear polarization state to another linear polarization state, and so on. So on the Poincare sphere, which I think I've kept it back here. Where is it? Oh, there. If you go to the Poincare sphere, you find that what it's doing is that on the equator of the Poincare sphere, it's going from one point to another. And that is the exact counterpart of neutrino oscillations, going from one flavor state to another flavor state. Yeah.
Ma'am, why are we solely focusing on two flavor oscillations, and is it possible to isolate one of the flavors from the others?
Okay, this is a theoretical physicist's trick. So suppose you want to understand. Let's move away from neutrino oscillations. Let's go to some much more mundane example. Suppose you want to understand glass transition. So as it turns out that if you take an absolutely pure system, it's much less likely to form glass compared to something which has many components in it. If you imagine the glass forming system as formed of hard spheres, if you have a compositional disorder, it's much more likely to form a glass compared to a pure system where all the spheres are of equal radius. So would you dive into a multi-component system with all its complexity from day one? No, you won't do that. So to understand the effect of this disorder, like having two different radii, it's enough to consider a binary mixture. A binary mixture captures all the essential physics, essence of the physics that you see in a multi-component system. So it's in the same spirit. Instead of going to a three-flavor neutrino description, it's enough to just restrict to two flavors and understand the qualitative physics. That's the sense in which.
Ma'am, can we isolate one of the flavors? Is it possible?
I don't know. Do you know if it's possible to isolate one of the flavors? One of the neutrino flavors, is it possible to isolate? I think this electron, muon, and tau, these three are there. And electron and muon, I think, are of relatively lower energy compared to the tau. Oh, yeah. Electron is, I think that is electron neutrino that is produced by the sun.
So what is produced in the sun is electron neutrinos. What is detected on the earth is also electron neutrinos. Okay. So when you detect electron neutrinos from a beam which contains both, you're essentially isolating the electron neutrinos. The muons are passing through because they don't see your detector. So the analogous thing for the light is that at the source of the light, you've got linear polarization. And at the detector, which is she called the analyzer, also you've got linear polarization. The source emits only linear polarization, and the detector detects only linear polarization. When you look at it after the Polaroid, you're looking at some linear.
So
now, what comes through the thing is actually circular polarization comes through unchanged through the sugar solution, but the two circulars come through with a slightly different phase, and that different phase depends on the color. So when you turn this Polaroid, you're seeing different colors depending on which one is the right thing that you are seeing here. So to answer your question, you are isolating neutrinos when you detect them and when you produce them. And the colors that you see are due to the fact that the phase difference depends on the color. And so the amount of rotation depends on the color.
Yeah.
Safe to say that when we are seeing one particular color, that there is only one neutrino present?
No, yeah, okay. This color and that, actually, the thing is that nomenclature of these quantum numbers are somewhat confusing. Flavor doesn't have anything to do with flavors. So colors, I mean, there's also a color quantum number.
Yeah.
So the polarization optics colors is completely different from the color quantum number or, yeah.
So to make it simpler, let's suppose that we had only a monochromatic source of light. You'll see nothing at all until you come to the right angle, and then you'll see the neutrino. And if you're at some intermediate angle, you might see some fraction of that. Now, the monochromatic example is the one that goes to the neutrino problem better, because at the sun when they're produced with some definite range of energies.
Yeah, so basically because we are using a white light source, we are seeing colors. If it had been a purely monochromatic source with one frequency, then you see perfect cancellation. In fact, if you notice this thing, I'll show you. Now I've got rid of the sugar solution, right? So to answer your question, so this is a polarizer. Oh, can it be shown? So here there's a light source and I've kept a polarizer, right? And now I have the second Polaroid and I'll just turn it. Here the light is let through. Now if I do this, this is cross polarization. So light is getting blocked. But it's not quite, isn't it? There's some blue light coming out. So that is because these Polaroids are also frequency dependent. And so there's some preference for blue light to get through. So that kind of, so we are dealing with a white light source, and that's the origin of the colors. If we had a monochromatic source, then you would have seen a perfect cancellation, and yeah. Yeah.
Ma'am, in the neutrino oscillations, can you comment on how the conservation of mass takes place? Like as the generation increases, the masses also increases, right? So how the mass will be conserved?
Mass conservation. Actually, I am not an expert on neutrino physics, so I can't comment really on these things. But if you, something about mass conservation. Yeah.
Suppose you take a superposition of two energy levels, yeah? And then you find that as it propagates, the energy goes back and forth between the two of them, right? So when you write down the Schrodinger equation, the conservation of energy will tell you that the expectation value of the energy is conserved, but even that is subject to the uncertainty principle in time. So if you have a purely monochromatic source, energy will be conserved for all time. But if you have two slightly different energies, the relative amplitudes of the two energy levels will cause you to go up and down in energy. But that uncertainty happens over the inverse of the energy. H bar divided by delta
Lifetime
E will give you a lifetime, will give you a time scale. Yeah. So it's consistent with quantum mechanics and the energy time uncertainty principle.
What is the time is still there? Yeah, this is, yeah. Oh, okay, yeah. That's right. That's something that we can do now. Yeah, so this is a movie that was taken of the demo from an earlier time. Here the colors are more striking. That's why we thought that we'll play this. So I think sometime back was having a conversation at the dining table with some of you, and they were asking about my view on physics and etc. So, and I was saying that I actually like to like to do the kind of physics that connects to experiments. Even if I do theory, I would like to make contact with experiments. And this is because there's an essential difference between mathematics and physics, which Sam had also talked about. A mathematical structure, a completely, entirely consistent structure, can stand on its own, and it doesn't have to connect to the real world at all. In contrast, in physics, no matter how beautiful the consistent structure is, if it turns out that it is not connects to experiments or it doesn't make sense, the predictions are not borne out by experiments, this whole structure is irrelevant. So that's why actually physics poses a much bigger challenge than mathematics, because of, and then I went on to say that that's why I like to stay away from fundamental physics, because fundamental physics has gone in a direction where the connection with experiment is very, very weak. I mean, it's hardly there in the most fundamental level. But this is an example, for example, a beautiful example of fundamental physics being borne out by observations and experiments. Neutrino oscillations, that was, the theorists had to come up with an explanation like this based on what they were seeing. And these neutrino oscillations have been borne out. And I think the Nobel Prize has gone to those people who have seen those neutrino oscillations. And not only that, one more point I wanted to emphasize is even if you can't probe at the fundamental physics length scales or time scales, you can do analog experiments. So this is an example. The polarization optics thing is an example of analog experiment, which helps you understand neutrino oscillations. So, yeah.
So, I mean, this whole story has an interesting, the angle to it. If you look at the development of this neutrino physics, there was a time when people thought that they had the standard model of particle physics. That's fundamental physics. So there were 3 generations of particles, at least that everybody knows. Okay. Now, what happened is that they were very satisfied with this situation, and within this standard model, neutrinos did not have mass. Although there were speculations earlier by people like Pontecorvo that the neutrinos did have a mass, the standard model said they don't have a mass. And then from the non-fundamental physics end of things, astrophysicists were trying to understand the sun. And they could look at the oscillations of the sun. This is not fundamental physics. This is very applied astrophysics. And they understood the sun so well by looking at it's called helioseismology, the way in which the sun oscillates when there are disturbances. They got a very good picture of the sun, and they've produced what they call the standard model of the sun. Now, the standard model of the sun was so good that they had complete confidence in their predictions about the amount of neutrinos coming in. But these models were not borne out by experiment.
So the observations challenged this beautiful theory.
Yeah. So
beautiful, elegant standard model theory.
Yeah.
So and then the theorists had to accept it and change.
So
their
it turns out
way of thinking.
That the standard model of the sun was right, but the standard model of particle physics was wrong. That was the final resolution. That shows the complete interplay between fundamental physics and applied physics.
And this is again making the point that no matter how beautiful a theory is, if it doesn't connect to your observations, it gets to be irrelevant. So this constant interplay and challenge from experiments keep theorists honest, and the other way around also. Theories give some life to experiments. So that's what the strength of physics is, according to me. I think I was having a conversation with you about this at the dining table. Okay, I think we can. Any more questions? 3:15 now. Yeah. Close to that.
Or general comments also welcome.
Yeah.
So I had one question. Like there are three flavors in general. There are three flavors. So how do you know which two flavors you have to choose? Like
How do you know which
which
two
two
flavors? Yeah, they're energetically lower. So electron and I think mu, these are the, you restrict to these two. Yeah. And low energy basically means that you're restricting to a, so like an effective point of view. Like that, low energy is typically what you would look at. You can probe more easily. That's why you restrict to the two lowest energy states.
Ma'am, in cross polarization, we noticed that when we put the second Polaroid, we can still see the blue light.
That's correct, correct.
But what if we want to block the light completely?
Yeah, so the thing is that this polarizer is frequency sensitive. So that's why it is preferentially letting out blue light. So you have to, yeah.
And what if we have to block the light completely?
Then you have to have the right kind of polarizer. Yeah, I suppose. Sorry? Mm-hmm.
Yeah, is it possible, or we'll still see some amount of light?
I think, yeah, with appropriate filter, it's letting out a certain frequency. You can have filters which can block out blue light and let out something else.
In the lab, there are polarizers which can block out this blue light
Yeah, in
also,
fact,
which work at all frequencies, but they come with a holder. It was a little impractical to use it in this experiment.
So Iqbal had actually suggested that. We tried only because of the holder, we couldn't do that. Then we could have blocked it. So that is a very good polarizer and also not frequency sensitive in this particular sense.
Any more questions?
So you just said about oscillation of sun. So can you explain a little bit about it?
It's not the oscillation of the sun.
Yeah.
It's about the oscillations of these neutrinos. A particular property of neutrino, which is this flavor.
What sir was mentioning.
Oh, is it
The
Sismo?
standard
Oh,
model.
okay, it's the Sismo thing that you can.
Yes.
Yeah, so see, they can measure by the Doppler shift, they can measure the velocities of the particles of the sun. So the particles of the sun emit spectral lines, and by looking at those spectral lines and their oscillations, they know exactly what frequencies are present in the sun. And these correspond to basically the eigenmodes. Just like here, there are coupled oscillations. You can take a complicated system which has oscillators and split it up into its eigenmodes. Just like here, there were two. The sun also has definite frequencies. In fact, everything, if I can pass that water bottle, just open it, will you? Yeah. No, more water. Yeah, she's got this frequency.
Kripa.
There's too much water in here. I'll try with this one. No, I'm sorry. Yeah.
Anyway, I mean, the point has been made. Yeah.
It's been made. Maybe this one will work. That's a frequency in here, no? Right? So in the similar way, all the frequencies which are present in the sun can be measured in the spectrum that you get from the atomic spectra of the sun. Right? So from that, they built up a model of the, what the sun should look like. That's called the standard model of the sun. And they understood the sun so well as to be very confident in their predictions that the neutrinos which should be detected in the Earth is whatever they had predicted. But the actual number seen here was about a third of that.
Sir, so as we know, every neutrino is oscillating around itself. So the tau neutrino in the sun, when it is oscillating, will it oscillate with other flavors when it is oscillating through the earth, or will it stay as tau only?
Isn't the, I mean, sorry. No, I was just thinking the sun emits only electron neutrinos.
That's right. The reactions that
the flavor oscillations are happening in the process of propagation between the sun and the earth. So the electron neutrino is getting converted into a mu neutrino and tau neutrino and so on and so forth.
It will also oscillate with the other flavors.
That's correct.
Yeah. The full matrix is a 3 by 3 matrix. Today we just had a 2 by 2 matrix, but the whole thing has got a 3 by 3 matrix, and that is the most general thing given 3 flavors.
So it won't stay as tau, but it will oscillate with every other flavor. Other two flavors.
It'll mix. It's called neutrino flavor mixing.
Yeah. In fact, the structure is like this, that I didn't discuss. If you take the 2 flavor thing, it's of the form, say, V11, V12, V21, V22, right? It's a 2 by 2 matrix. And if you take the 3 flavor one, it will be of the form, say, V11, V22, V33, and V12, V13, V21, V23, V31, V32, V33, right? So what happens is that, if I just restrict to this for the moment, these off-diagonal elements are responsible for mixing the flavors. So these are the things crucial for
I have one more question. What is leading to the oscillation of these neutrinos in the sun? Like, is this the energy inside the sun, or?
Oh, you're talking about the inside the sun. That is a different thing. That's a different physics, right? I'm just talking about the neutrino oscillations. This I'm entirely talking about the neutrino flavor oscillations between coming from the sun to the earth. So that oscillation is actually guided by these off-diagonal elements. These are called, I feel that mixing is a slight misnomer, but the reason is that, okay, maybe I won't get into that, but if you take any quantum mechanical state, it's a coherent superposition of 2 states, right? And these off-diagonal, these amplitudes are the things that are responsible for this coherences. And these are contained in these off-diagonal elements when you construct such matrices. So the things which are responsible for superposition of states.
Passes through a vacuum, it's got a certain refractive index, which is 1 and independent of frequency. But when it passes through glass, the refractive index depends on the frequency. In the similar way, when neutrinos come through empty space, they have this 3 by 3 matrix, which you wrote down. But inside the sun, they have a different 3 by 3 matrix, which depends on the density of the matter, the kind of matter, all kinds of things. It's more complicated within the sun. And even that has been understood by the people who do these things.
Yeah. So if you look at this Poonam's paper, you'll get a more concrete idea about what are the, here I've just written schematically, what are the things that are involved in these matrix elements. That will give you a much better idea, understanding of the physics behind neutrino oscillations. Yeah. Okay. Yeah, that's right. This is around the big time. Okay, thanks. Thanks for your attention.